Good afternoon, everybody. Welcome to the fourth session for the GSE 102 at the 2021 GSE Virtual Conference. Hope everybody's doing well. And yeah, I said good afternoon, but perhaps it should be a good morning or good evening, depending where in the world you are. So for our fourth session, we have Keith Sisson from BMC giving a presentation on Fetch, how zOS uses linked list, LPA, steplib, and catalog to find and execute programs. If you have any questions throughout, if you could please put them in the chat, and I'll field them to Keith. At the end of the session, I'll be putting a link for feedback in the chat window. If everybody could please make sure to give feedback on the session, it's really important, so we can try and make the conference as good as possible. Without further ado, Keith, over to yourself.
All right, great, thank you. Yes, and good morning for coming to you live from Detroit, Michigan. It's currently 9 a.m. in Detroit. Weather, I think, is pretty much similar to what you would be finding in the UK or wherever you happen to be from. I hope you're all having a great day. So this is the first time that I've given this particular presentation, and I'm hoping that you will really find it interesting. And it's a bit of a challenge with Zoom because I don't get instant feedback from looking out at the audience. So please do enter your questions or comments in the chat window anytime you want throughout the whole thing, and David will relay them. It really helps me to make sure that you all are on the same page with me and that we're having a great session. So the session name, yes, Fetch. Its session number is 6BB. And again, please, at the end, give me feedback, give us feedback. I really want to know if you found this valuable and interesting. So also, I wanted to mention that there is a charity raffle that you've probably seen in many of the presentations for a couple of great charities, the RNLI and the Guide Dogs for the Blind, great charities. And so consider signing up for that raffle. It's a great cause. So with that, let me go ahead and start. So Fetch, what does that mean? This is my dog running in my yard. His favorite game is going out and fetching something, going out and bringing it back. So, but what does that really have to do with zOS? So let me kind of set the stage. And I want to set the stage so that everybody is on exactly the same page and we can move forward and we have good understanding. Okay. So what we're going to cover is, where does zOS fetch programs and where does it put them? So this probably begs the question, why are we fetching programs in the first place? What are we trying to accomplish? So let me go into a little bit more detail about what that is. So program fetch is, strictly speaking, because you want to execute a program. So all computer systems are basically ones and zeros. There's really no magic behind it. If you want to execute a program, zOS has to go find it. They have to fetch the program and get it into your address space. So it has to go out and get the program that you want to run and want to load it into your address space, and then it can execute the program. Okay. So all this fetching and putting happens for you by zOS, but zOS is very specific about where it looks. So I'm going to try to demystify this whole thing, and hopefully you'll find it interesting. And spoiler alert, that the system takes care of all of this hard work, but it's still necessary to know how it works in order to move forward. So I'm going to start with the very basic beginning here, and that is, what is an address space? So if you think of an address space as a giant Excel spreadsheet full of blank cells, you can kind of visualize what an address space is. So the size of this address space is 16 exabytes. That's 1 million terabytes. That's the number of addresses that can be generated with a 64-bit address. Meaning if you start over in the bottom corner here with all zeros, 64 zeros, you're down here, and address all in the top is 64 ones. That's 64, that's 16 exabytes. So it's a enormous amount of memory. So one of the things that you should kind of know about an address space is no computer system has 16 exabytes of real memory. The mainframe, can have 10 terabytes or more of real memory, but that's a really long way from 1 million terabytes. So an address space is really virtual memory. Virtual memory is an illusion that is created by zOS, and it wants to create the impression that there's more real memory than there actually is. So even though you can address 16 exabytes for each address space, there's really only a fraction of that available in real memory. So what the system does, what zOS does then, is swaps code in and out seamlessly behind the scene, in and out of real memory in real time, to give you the impression that the entire program is loaded. But in actuality, only thing that's loaded are the instructions executing and maybe the look ahead instructions that it thinks that you're going to need in the future. So the memory, the address space itself, when it is first created, and everything becomes an address space, a TSO ID, a batch job, CSS regions, DB2s, system started task, all of that start out as an address space. And they're all created equal when they're first set up. And they're mapped out something like this. So there are various areas where the system, based on what the system programmer says, loads things into this address space for you. So the address space doesn't come to you blank. It comes to you preloaded with certain data areas and programs and other things that the system needs to use it. The reason that everybody gets an individual virtual address space is so that your address space is unique and things that happen in your address space won't affect someone else's address space. So it's one of those elements that contribute to the 5 nines or more of reliability that System Z and zOS has. All right, so there's a couple of historical notes that I want to make about an address space. Originally, many, many years ago, the address ability of zOS was 24-bit. So with 24 bits turned on, the biggest number you can get to is 16 megabytes. So there was a line. So the address space used to only be 16 megabytes in size. So there was a variety of things that were needed for the operating system that are still there even today, but they're mapped out below the 16 megabyte line. Then as things advanced, a 31-bit address was created, and that nomenclature is known as the bar. So they had the below stayed the same, and they extended above up to the 2 gigabyte line. Again, 31 bits gets you 2 gigabytes of addressability. Okay. So now the reason this was done was kind of a genius methodology from IBM. And I know my friend Bob Rogers had a lot to do with creating this extended architecture. And if you ever have a chance to hear Bob Rogers speak, you should take it. He's a brilliant and funny man and does great presentations. So anyway, in this configuration, the reason that IBM did this is so people didn't have to change programs. If they wrote a program that used 24-bit addressability, it simply used the system below the line. And if they wrote a new program or they changed the program to use 31, then it could use this extended area. So the idea was they didn't force customers to change anything. They could continue on without a disruption to their business. So they could continue using more modern technology, more modern hardware, more modern everything without massive changes to their programming, which means they could adopt the technology much faster. So of course, now the modern system is 64 bits. It's been that way for quite a number of years. And you'll also notice that this isn't really to scale. So up here in this shared user area is it's 512 terabytes. Okay, so 512 terabytes is a long way. There's a big amount of space here between 500 terabytes and 1,000,000 terabytes up to the 60 megabyte line. So this high user region is enormous. Okay, so what happens is when your system programmer defines some things, and I'm going to relate this back to fetch now. I just wanted to give everyone a level set on address space. When the systems programmer will define certain characteristics of this address space for you that's loaded in the beginning. And what they will do is they will specify things that need to be loaded in PLPA, and I'm going to go in LPA in general. I'm going to go into that, what all this means in a minute, but I just wanted to show you, give you a kind of a visual that the systems programmer loads things into this area. So every address space when it starts has these things loaded in it when it is started. Okay. So I know that was kind of a lot, first thing jumping right in, but I just want to make sure everybody understood we're fetching something, where we're putting it, and why it's important. It's important because you can't execute something unless it's loaded in your address space. All right. So we're going to focus on those things right in a minute so you can understand what's going on. So this user space that I have an arrow next to, an extended user and high user, are all areas which are known as private areas, which you're free to use as a developer or a coder. You're free to use those to load and do things in your own address space. Okay. All right. So again, you can talk about address spaces and virtual memory and a lot of things, for a long time, but I wanted to set a good foundation so that we didn't lose people where we are right off the bat. So if you say this is starting at address 0 and going to 7 fox, this is a memory map of what a zOS system might look like. And I just wanted to throw this out that starting in byte 0, there is a map of what this address space looks like. And the map is a set of control blocks or address ranges that you can use to figure out where certain things are on the system. Now, the reason that there has to be a map is because it's up to each individual shop to figure out what exactly they're going to load into LPA, how exactly sized they're going to make their CSA or SQA, and they'll have different devices. So their nucleus and SQA and all these kinds of things will be different. So the memory map for every address space is unique for every customer. So the thing that is the same though is starting in address byte 0, there's always a map, and that map will point to the various areas that you need in order to, the system needs in order to operate. So just a touch on that, just in case that it's interesting. So I'm going to back up a little bit. I'm going to talk about this in relative terms to JCL. And this is a 102 session, so I'm assuming most of you have a background in JCL, but just in case, I want to make sure everybody's level set. JCL maybe looks a little bit foreign because of the slashes in column 1 or whatever, but it's really a quite straightforward thing. There's a job card that identifies who you are. There is an exec card that tells the system what program you're going to execute. There's a variety of DD statements that define files that are needed for the program. And there are perhaps some commands that you pass to the program. And then there can be multiple steps in the program. And notice this step has a step live, and I'm going to describe how that fits in the example. I just want to make sure, in case I'm assuming that everybody has a background in JCL, but there it is. Okay, so fetch order. You want to execute this program. You want to execute program execel. Now, how does the system find it? Where does it know to go get it? And what does it do with it? Well, it has a particular order that it uses to find things. And here is the order. Okay. So the order is Jobpack area, Taskline, step live or job live, LPA, or libraries in the linked list. So I'm going to go through them each one at a time to describe what they are and how they're used. So before I start getting into things, David, was there anything that came up in the chat that people had questions about, or everybody seemed to be on page? Maybe
no questions. Everybody intently watching. I will. I've got my eye on the chat window, so I will field anything that comes up.
Okay, good. Just want to make sure. All right, thank you. Okay, so let's start with the Jobpack area. Okay, the Jobpack area is something that is checked first to make sure that you didn't already load the program into your address space. So if you have an address space and the program was previously loaded and it wasn't overlaid and nothing was touched on it, the system is going to just reuse it. No sense in refetching it if it's already there. So that's all handled behind the scenes and it's invisible to you. So that's just a note. If it's already there, it uses it. If it doesn't find it, it's gonna request a new copy and put it in the system. So if you say, execute this program and it's out there in an address space, it'll use it. Okay. So the second part is the Taskline. These first two are kind of invisible options. They aren't something that are typically set up by the systems programmer. So it's not common that people think of JobLive or Taskline. So I'm gonna show you what Taskline is. Taskline is actually something that a developer of an application can use. It's a macro, it's an assembler macro that can be evoked, and it can tell the system programmatically where to find something. So if you're executing a program and it comes along and this code, this is the assembler macro or a sample assembler macro. What that says is, I want to execute this task A, and I want to find it in this task live 2. That's a DD concatenation. So if you're running JCL and you have this concatenation of data sets, and the program that you're executing tries to attach that program, it is going to look in these two data sets for it. Okay, so this is something that is controlled on the application level. It's not, I don't know if it's commonly used or not, but it's not something that a systems programmer per se has control over. So a lot of times Taskline is forgotten about. All right, so the third thing that we're going to talk about here is step live and job live. Okay. Step live and job live are DD statements that are included in your JCL. So they are specific concatenation or single data sets that are used that are then searched ahead of the rest of the default search order options that we're going to go into. So those other default search level options are bypassed essentially by using step live and job live. So again, it's the same thing. It's looking for whatever you had in your exec statement, whatever your program parameter was pointing to. If it doesn't find it in that library, only then will it continue the search and search for the system, other system libraries. So I guess what that means is, if it's in there, it will use it. But if it's not, it doesn't stop. It continues on to look in the other areas that it might be able to find and fetch the program from. So this library in the step lib, job lib can be a PDS or an extended PDS, PDSE. So either one of those are valid step lib or job lib types of data sets. Okay. You can also have a step lib and a job lib in the JCL. And if you're doing that, you have to be careful because only one or the other is used. So if you specify a step lib and a job lib, the system ignores job lib for the step that says step lib. So sometimes people can be confused with that. And let me give you a little bit of example. In this top example, we're looking for a program SPK-CH. It's going to search in this priv.lib5 dataset. If it doesn't find it, it's going to look in the rest of the system areas that it would normally find to try to find that. Same with this second step, this step 3. It's looking for TIL80. It's going to go to this priv.lib12. Doesn't go back to lib5. It's just for this step that it's applicable to. But if you look at the bottom step, we've specified a job lib. By specifying a job lib, what you're saying is every step in this JCL, every program execution is going to look in this group4.load lib in order to find it. So step 1 and step 2 for SNZ12 and snap10 are both trying to find those programs in that load library. But if you go to step 3, there's a step lib. It will no longer search for the job lib. It will only pull modules out of the load library that you specified in this case. So it overrides it. Job lib really has to be the first statement after the job card for it to work. And you can't have any other statements between the job lib and the step lib, or the job lib and an exec, or it won't work. It has to be in the top in order to execute. All right. So the next section that I want to talk about is LPA. Now remember that this is already loaded into your address space for you. Okay. So the LPA is link pack area, and that comes, this is generally speaking from sys1.lpa lib, but I'm going to go into each specific segment of the link pack areas and talk to you about how those are configured, just to remove any, mysteriousness about how those things are done. But essentially what we're doing is we're taking a defined set of modules and libraries, and we're loading them into the address space primarily at IPL time. Okay. So I'm going to also caution that things that are loaded in LPA at IPL time are persistent, meaning the system doesn't reload them automatically when you IPL. Once they're loaded in there, they stay in there until you tell the system that you want to change LPA. And at IPL time, it's a CLPA command to change it. So if you don't do a CLPA, even if you IPL, these LPA members stay the same. Most shops, or many shops, automatically do a CLPA so that this reloaded at IPL time. Okay. So within LPA itself, this link pack area, it has its own search order, so that when you find a module, as soon as the system finds it, it stops looking for any other copies of it. So you can think of it as, if you have it in a step lib, it'll pick the step lib and doesn't bother searching anything else. Same with LPA. If it finds it in a particular order, even if there's multiple copies of that same program, it will pick the first copy that it finds and use it. Okay, so the area here then are the dynamically added LPA modules. This is the first in the search order. So if you dynamically add an LPA module, it will be loaded first. And that is done with a system command after IPL, usually shortly after IPL as part of the system coming up. It executes this LPA add with a specific module in a specific library that you want to add it for. You can do this at any time. You know, dynamic LPA is sometimes people just automatically do this, and sometimes the systems programmer wants to put a new module in, so it will dynamically add it sometime after they IPL to fix an issue or to make some changes that they want. But it's the first thing that's searched for, and it's done by a system command. The second area that is searched is the fixed LPA, FLPA area. The FLPA area is defined in sys1.powerlive by the systems programmer in this IEA fixed XX member. So that looks like this. It says include from this module, sys1.lpa lib, these individual modules. Okay, so the reason that you would use fixed LPA is because you want to capitalize on the fact that these modules are loaded into your address space and are not paged out. Remember, in virtual memory, things can be paged out and paged in. Now, it happens almost instantaneously when something is being executed that it's swapped back into the address space. That happens almost instantaneously. But if you have a module and it, by not being paged out, it significantly increases its performance, then you would include it in here. I think these are examples of RACF modules that are included because they're highly executed and they don't want to be, they want them to be always available in the address space. So that's why you would use the fixed, and that is the order that it will find it in. So if you put something in fixed, it will do this. Now you want to be judicious on the number of modules you put in FLPA, because obviously they're fixed and they're not paging out. So it will take real storage to accommodate those. The next area is the MLPA. It's just below the FLPA when the system is searching. So it's generally, you know, a temporary add or, you know, a replacement for an SVC routine or something like that, that you would use the MLPA. It happens at IPL time, so it's not something that dynamically changes, but that is controlled with an include statement as well in the IEA LPA XX member. So you can include particular members that you want to include from a particular library that you wanted to include it from. Okay. Now, the next area is the full-blown pageable LPA. That's defined in LPA list or a prog XX member, as the systems programmer would in sys1.powerlive. So that is simply a list of data sets, almost always including sys1.lpa lib and other things that demand excellent performance. So that is the LPA list order. Now, remember that when the system is trying to execute something on your behalf, or you could have loaded programs in here that are usable, that are, you know, private programs that you have written. They could also be loaded into PLPA. They have certain requirements. I'm not going to go into them, but they have to be something called reentrant, and I'm not going to really talk about that because it takes me off on a whole different tangent. But they have certain requirements that they have to meet in order to be in LPA. The point is, they're already loaded in your address space. So when you go to execute them, there isn't a big, long fetch process to find them and to understand where they are, okay? My point of going into so much detail on these is nothing is mysterious about this. This is just something that the systems programmer decided by experience needs to be there for performance reasons and to keep the system operating at its peak efficiency. Any questions on that before we go on? I see there's nothing in the chat, but I just want to make sure.
Yeah, no, nothing's come through.
Okay, all right, great. All right, so the next area that you can find something is the linked list. And the linked list can be a little bit more complicated because of its historical evolution. So the linked list is a list of data sets. It's a list of load module libraries that are on disk. So the system, if it didn't find it in those other locations, it's going to search the linked list. So the problem of loading something from disk is that I/O from disk is slow, relative to memory speeds. I/O to disk on the mainframe is extraordinarily efficient and very fast. And one of the hallmarks of zOS is how fast it can access disk-based data. But it's still slow relative to memory speeds, especially speeds when the module you're trying to execute is already in your address space. So I'll go into how zOS has evolved over the years to improve that performance. But let's just say the linked list is just a concatenation of load level library modules. There can be a PDS or PDSE. So when I say concatenation means if you list a set of data sets together, it is considered as if it were one continuation of the first data set. So in order to improve performance, like I've said, there's two kind of functions, LLA and VLF. Those are used to really greatly improve performance to locate these modules. And I'm going to explain how that works in 1 second. All right, so before, let's just say the linked list libraries are also specified in sys1.powerline, and they're a prog.xx member or a linked list XX member, and includes sys1.linklib, miglib, csslib. These are what commands would look like in the prog.xx member. It's just saying, I'm going to create a linked list. In this case, the linked list is called base IPL. I'm going to add command line, haslink, hasmig, CSE run, my language environment. So these are just an example. You could have hundreds of data sets in this concatenation, and all of them will be searched in the order that they are listed in this thing. So if something is in command line, and also an SE run, it'll find it out of this order first, whatever the order was specified in here. Again, though, it takes a long time to read through hundreds of data sets to find what you're looking for. And when I say read through, what I mean is it has to go to that library on disk. It has to look at the directory entry for that library, and it has to search that directory entry for the module that it's looking for. And it does that for each data set as it goes through. So the farther you are down the list, you could see where it would have had to have done a lot of I/O before it got there. Now, it doesn't do that anymore. This was 100 years ago that it actually did that. LLA has been around for a very, very long time, and I will explain how LLA improves the situation. So LLA, library lookaside, is a zOS function, and it is a system started task. So what it does is it maintains a copy of the directory entries for the disk, for the data sets. And it looks at what cylinder head and record, where those modules actually live on disk. So what it does is when it first comes up, it caches all of that directory entry to determine where on disk it actually is. So it reads all the data sets, it reads the directory entries, and the directory entries identify exactly where that module is on disk. And it caches all of that memory into its own address space. So now what happens is when you want to get the module, when you say, I want to execute a program, XYZ, it goes to the LLA cache and says, is XYZ in your cache? And if it finds it, it says yes. And here is the exact location on disk that is. So it avoids all the directory lookup and the directory search. And it does it really quickly because it's simple. It's a simple lookup table. It's the name of the module and where it is. Boom, it goes directly to that disk, reads that module, pulls it into your personal address space. It fetches it from that disk, pulls it into your personal address space, and then it starts executing it. Okay. So as you can imagine, this can cause a problem. And the problem is that if someone updates a data set after the system has loaded the entry of where it is on disk, if someone makes a change, recompiles or reassembles the load module into the library, it's likely going to move somewhere else. It's not going to stay in the exact place it was on disk. So what happens then is when the program is asked to be fetched, it's found in the LLA directory, but it no longer matches the right location and something wrong is loaded back and tried to execute. So you're going to get abends. I think it's a 107 abend, but you're going to get an abend that says this is not a valid load module. So in order to correct that, though, there is a simple command that you can execute. So if you update a data set that's in the linked list concatenation, you have to tell LLA to reload the directory information. And that is the famous LLA refresh, or that LLA refresh refreshes the entire list. LLA update allows you to specify certain libraries that you only want to refresh their directory entries for. So it's a simple workaround, but sometimes it's missed when a linked list data set is updated. You have to do an LLA refresh or an LLA update. Okay. So it's still an IO to disk to load the module. Much quicker that it doesn't have to do the directory lookup, but it's still an IO to disk. Okay. So then there enters another facility called VLF. VLF is another address space. It's the virtual look-aside facility, and it is also designed to improve performance. Now, it works with other things besides LLA, but in this context, we're going to talk about how it uses LLA. But really what it is it's an address space, and it manages some of that data space in that 16 exabyte address space of its own to store frequently used data, let's say, frequently used data. And then when the application makes a request for that data, VLF checks its own address space to see if the data is there. Okay, if the data is there, then VLF can transfer memory to memory, whatever that data is. It doesn't have to do an IO, excuse me, it doesn't have to do an IO to DASD to do it. It's memory to memory. So it's a much quicker fetch, memory to memory. So LLA in particular uses VLF to store modules. They store the actual modules instead of them being on disk. They store it in the VLF address space. Okay, it can be used. It's obviously being used by LLA, TSO, catalog address space, RACF, all sorts of applications can use VLF. So it's not solely just modules, but in our context, LLA uses it to store modules. Okay, so instead of just loading directory entries into LLA, it's loading the actual modules into VLF so that they can be fetched much faster. That is also in sys1.parm_lib, and you can tell it the class of service that you want to have. And this is a simple definition, an example of one definition of telling it LLA is going to use VLF. Okay.
A question for myself, actually, Keith.
Yeah.
Under what use case is it? Sorry, not use case. Is it an easy choice between using VLF over LPA? Is there kind of a set, almost like walkthrough you would take to decide which one to use?
So it's kind of a rule of thumb around LPA is that it's really designed for things that have to be extraordinarily fast, and it's usually system related. You're usually putting in LPA something associated with CICS or DB2 or RACF, something that drives your entire system and requires, you know, enormously quick response time. So because it's in LPA, you know, it gets premium service, but there's a limited amount of space that you can use because you only have a certain amount of space in your address space to use for that. So you have to be a little bit judicious about what you put in there. So most application code actually runs in linked list and then is utilized by LLA and VLF, because typically if a batch job, for example, is running and executing a program, if it takes a millisecond longer for it to load the program execution, it doesn't matter much. But if you have an interactive user that's doing a CICS transaction like a credit card transaction, you know, that has to happen instantaneously. So you would consider using LPA for those libraries, for those modules to make them more efficient.
That's great. Thanks very much.
Okay. All right. So I guess the last part of this that I didn't really cover is how does the system find libraries on disk? And I just wanted to close the loop on this by going a little bit more into what the catalog does and how the catalog works. So that's the whole is, you know, where does this system find the data sets on disk in the first place? So the catalog becomes an enormously important part of the way an entire system operates. So a data set is cataloged, and so that you can refer to it by name without needing to know where it is. That's the definition of catalog. You just say, I want this data set. The system looks at the catalog and tries to find it based solely on the name of the data set. So zOS, in order to ultimately find it, needs to have three pieces of information. It needs to know what the data set name is, the fully qualified data set name. It needs to know what volume it's on, and so it needs to know the valseer of the disk unit that it's associated with. And it needs to know what the device type of that unit is. So whether it's a DASD array or a tape or other kinds of things. So the unit is important for it to know how to get that information. Okay, so data sets can be cataloged or uncatalogued. If you uncatalog a data set, or if a data set is not cataloged, it doesn't mean it doesn't exist anymore. It just means the system can't find it with the catalog. So if you're trying to access a data set that is uncatalogued, you have to supply the data set name, the valseer, and the unit type in order for it to find that data set. You might have an uncatalogued data set. Most application type systems would not have uncatalogued data sets routinely. This would more be like a tool for a systems programmer when they have sets of identically named data sets and they want to operate on the uncatalogued version before they put it in production, they might have two copies of it. One is uncatalogued and one is cataloged, because you can't have two data sets of the same name cataloged. You have to pick one or the other. So that's why you would have an uncatalogued data set. So if a data set is SMS controlled or system managed storage controlled, it has to be cataloged. And that usually happens at the disk level, the volume level. Any data set on a particular volume that's SMS managed, system managed, storage controlled, has to be cataloged. Again, system managed storage is a whole nother hour-long topic, but let's suffice it to say that there are a lot of controls that you can do over the data sets if they're system managed, or controls over the volume too. Okay. So catalog data sets uses the system catalog to store and retrieve the unit and the volume. So all you need to know is the name of the data set. All right, so I'm going to go into a little bit about how that's defined and a little bit about how that works and why you would do it a certain way. Okay. So in zOS, there is a master catalog and there are user catalogs associated with it. They store the locations of the data set in a pretty simple lookup table. So you have to have at least one master catalog, but no one operates with one single master catalog. Everyone has user catalogs associated with the master catalog, and they have a relationship to one another. And I'll kind of describe that in a second. The reason you do that is you can have tens of thousands, hundreds of thousands, millions of data sets. And if you had them all in one catalog, the catalog would be enormous. But by splitting them into multiple user catalogs, you really improve efficiency. And you also can improve logic. I'm sorry, not logic, but you can improve performance, because it's not always hitting and reading and updating one catalog. Because remember, everybody that allocates a data set will ultimately create an entry in a catalog for that data set. If you create a catalog data set, the catalog has to be updated. So depending on how often you do that, it can cause bottlenecks. So you don't really want to do that. What you want to do is define aliases in the master catalog and relate them to user catalogs. So you can see in this example, I have defining an alias, and the alias name is prod, and I'm relating it to user cat1. Okay, so user.cat1 is the name of the user catalog that I'm doing. It's a data set. And prod is the high-level qualifier. High-level qualifier being the first up to 8 characters. So any data set that starts with the characters PROD, the system catalog is going to go to the user catalog to try to find those data sets. Same thing with the second example, test. Any data set that starts with TEST is going to go to user cat2 to try to find that data set. So here's an important distinction. If there's no alias for that data set in the master catalog, then the data set is actually cataloged in the master catalog. So all this cataloging function happens automatically in the background. And it's used with sample, and you can do it in JCL, and here it is. In this example, I'm creating a new data set, prod.inst.cntl. I'm telling it I want it cataloged. I'm giving it the space parameters, and the system picks the valseer based on this unit type. It picks the valseer, creates this data set with this certain size, and it creates a catalog entry for it. Okay. So now what I want to do.
Sorry, yeah, it's a 10-minute time check.
Okay, great, thank you. I'm just about to wrap up, so we'll have some time for questions at the end if there are any. Okay. All right, so let me just show you what I mean by that. Sometimes a visual example is easier to relate to. Typically, data sets that are at the system level are cataloged in the master catalog. And the reason that is early in the IPL, user catalogs may not be available and only the master catalog is available. So in order for the data set to be found early in the IPL, it has to be in the master catalog. So in this particular example, you can see I have a data set, sys1.a, and it's cataloged in the master catalog, and it says that it's on volume prod 900, right? So when that data set is referenced, and that data set could be sys1.lpa live or sys1.see run or some other important system level data sets, it finds that data set on that disk and does all of its early operations, whether it's loading it into LPA, whether it is authorizing the data set, whatever it's doing that it needs access to that data set early on, it finds it with the master catalog entry. So the second example I have on here is prod. So remember, we created an alias for prod. So it's an alias entry, and it says to go to user cat1 for its information. So starts at the master catalog, sees that it's in user cat1, goes to the user cat, prod dot, say I want to try to find the data set prod.list.backup. So it goes there. Now look, it says, oh, it's on a Valseer of 777555, which is a virtual tape subsystem. So that means I need to mount a tape and ask for that particular file to be loaded. And there it is, prod.list.backup, and it can be read in that way. That's how it knows where to go to get it. Same thing with if I was looking for prod.install.cntl, finds the prod high-level qualifier, goes to the prod install control, and goes to the particular volume and finds it on that particular volume. Same thing with the test user cat, goes to a different user catalog, goes to a different Valseer, finds the data set and accesses it that way. And then the final example is a test file there. But notice sys1a and sysb, it knows exactly where it is. It's in the master catalog. So that's the differentiation between why you would have it in the master catalog and why you would have it in the user catalog. Now there's commands that the system uses to relate these catalogs to the master catalog so that it knows where they are. And the catalogs are all of a particular data set type called a VSAM data set. And they're formatted in such a way that the performance is very quick in doing the data lookup for that information. Okay, so I hope that kind of put together the entire picture of where a data set was found, how it was loaded either into LPA or accessed with the linked list or accessed with a step lib, how it finds all of the things that it needs and load your program so that you can execute it. So I know that things that happen behind the scenes can often be mysterious. So I'm hoping that that helped take some of the mystery out of it. So any questions, anything that I can review right now, anything that was a little fuzzy that we can go over? All right. Any comments on the level of information that I went to? Was it too much detail, not enough detail, too high level? Anything that we can think about from that aspect?
Well, we've got a question from Mark. Could you comment on link auth equals linked list?
Sorry, can you repeat the question, David?
Yeah, sorry, it's a question from Mark. Could you comment on link auth equals linked list?
Link or link list?
Link auth. Sorry.
Oh, link
LNK
off.
or.
Oh, okay. Thank you. All right. Sorry about that. So authorization, APF authorization is something that is tricky at a location. Anything that is an LPA is automatically considered authorized. You can specify a linked list as being everything in it is authorized by default, or you can not have things be authorized in the linked list if that's what you prefer. Many of the locations that I've associated with do authorize everything in the linked list by default. But that's kind of a security / systems programmer question.
Thank you. Another question from another Keith. If a load module is not found in the tasklib DD, are the system libs searched instead?
Yes. If it's not found in the Taskline, then, oh no, the actual program will fail if it's not found in the Taskline. So if you code the assembler program to say, load this module from this Taskline, it won't go anywhere else and find it. You'll get an error in the application.
Great, thank you. Then some feedback from Donna and Wendy saying it perfect and great for me. And I'd echo it as well. I think the level of content was absolutely spot on. So thank you very much. Are there any more questions?
Okay, great. And now make sure that you do go and supply the feedback. Give me a rating. Be honest. I want to make sure that I improve the presentation for the future. So please, click on the link. I think that David might be pasting this link into the chat so that you can click on it easier. But session 6BB, it only takes a second, and it really does help me, and I appreciate it if you do it. And then there is some information on becoming a member of GSE UK. I've always loved GSE UK, especially for their focus on people new to Z. They do a really good job with the 101 and the 102 programs. So I think most of you being in this presentation are probably already a member of GSE UK, but here is the information for them. So I think with that, we are out of time. And I really appreciate everybody's participation, and I look forward to talking to all of you in the future at some point. So thank you.
Great, thank you very much for the session, Keith. Yes, if everybody could. Oh, sorry, we've got one more question. If you're happy to take it, Keith, just the last 2 minutes. In what context does it make sense to use freeze of linked list?
Oh, that's a tricky one. I don't know that I can give a really good answer for that right off the bat. So I know there is a checkpoint freeze option. It's not something that I have spent a lot of time using or working with. So I apologize that I don't really have a good answer for that, for the freeze option. Sorry.
Okay,
I don't want to give a misleading answer.
Thank you very much. If I could encourage everybody on the call to please give feedback. I've provided the link in the chat. And with that, Keith, you happy with me to close the session?
Yes, let's conclude the session.
All right, thank you very much, and thank you very much all for attending.
All right. Thank you very much, everyone. Bye now.